I wanted to give you a little feedback on what I saw in grading your papers for the electrolyte lab day 2. And the biggest area where I saw problems with your papers was in connecting the drawings that relate to zinc metal reacting with different acids. Most of you had the equations correct. So in the first example, zinc is reacting with hydrochloric acid. Well, zinc is a solid. It is the elemental substance. That elemental substance has no charge. So I'm not going to put a +2 above that zinc because this zinc has not reacted yet. It is still the elemental substance, a piece of zinc metal. Now around that zinc metal, we have the strong electrolyte, hydrochloric acid. So what does strong electrolyte mean? I fully dissociate into ions. So I have some H+ ions and some chloride- ions. I don't see any intact molecules of hydrochloric acid. Now these two react, and as you saw in the videos, there were some bubbles, and those bubbles correspond to hydrogen gas being formed. As well as you didn't see any solid precipitate because the other product, zinc chloride, is soluble. So I'm going to do what I normally do, which is underline things that are solid, liquid, or gas and tell myself these things do not dissociate. So in the product beaker, I'm going to make some H2 gas bubbles, and those molecules actually leave the beaker. They're the bubbles that you see forming. And in the solution that's left in the beaker, we have some zinc ions and some chloride ions. Again, fully dissociated because zinc chloride is a soluble ionic compound. Charge is important, zinc 2+, chloride -. I don't see any intact zinc chloride molecule because it is an aqueous ionic compound, which means it fully dissociates. Strong electrolyte. That's a little different than the other situation you were given, which is zinc reacting with acetic acid. So in this case, I still have zinc metal. Zinc still doesn't have any charge, but I have a weak acid. And I encourage students to circle weak acids to tell themselves these largely do not dissociate. So I'm mostly going to have intact acetic acid molecules with no charge in solution. But every once in a while, one of them will dissociate. So I'll get some H+ and some C2H3O2-. That's what weak electrolyte means, is that it's not fully dissociated. Mostly I have the molecule. Sorry, this wasn't the clearest writing on my part, so I'm gonna try to clear that up. But I do have some ions in solution. Again, these go to form H2 gas, and this time the soluble compound zinc acetate. Again, that H2 gas is going to leave as an intact molecule. And in solution, I'm still going to have some zinc. But this time, the ion is the acetate ion. Again, I don't have any intact molecules over here because molecules of zinc acetate, because zinc acetate is a soluble ionic compound, so it fully dissociates. While this solution may have been poorly conductive because there are few ions, this solution is going to be highly conductive because everything's in solution. Now, what you did observe experimentally, and what is certainly true, is that this reaction goes a whole lot slower than this reaction. And you were asked to explain why. And what I really wanted to see in your explanations was some description of this reaction needs H plus to meet the metal surface. Or you need those ions. I was looking for some description of the fact that the reaction is faster with the larger amount of H plus ions. I forgot to write your, sorry, I'm getting ahead of myself or behind myself, whatever you want to say. I forgot to write the NIE for the reaction above. If you'll notice, I underlined everything that was solid, liquid, or gas, and I circled everything that was a weak electrolyte. So when I write my NIE, all of those things stay the same. They do not dissociate. The only thing that dissociates is that zinc acetate. So zinc 2 plus and 2 CO3 minus. Or sorry, not CO3 minus, this isn't carbonate. What am I saying? 2 acetates. 2 C2H3O2 minus with aqueous. Whereas up here, I also didn't put my NIE. Everything that's underlined, solid, liquid, or gas stays the same. So we're going to have zinc and hydrogen. And then I need to have a balanced equation. So on the left-hand side, I need a source of hydrogen. So I'm going to have 2 H pluses. And on the right-hand side, I need what happened to the zinc, and that zinc became zinc 2 plus aqueous. So that's a different NIE. In this reaction, in this NIE, you see you have available H plus ions. They're right there. But in this NIE, you see you mostly have molecular acid. You don't have those H plus ions that are needed that make that reaction faster. Now, why are the H plus ions needed? I sort of skipped the part of your chapter 4 or 5, I've forgotten now, that talks about redox reactions, but zinc itself has no charge. It has an oxidation state of 0, but zinc in this compound has an oxidation state of 2 plus. So zinc loses some electrons. And who gets those electrons? Well, in this formula for the acid, the hydrogen has a +1 oxidation state, H plus, it's the source of my H plus, but hydrogen gas, elemental hydrogen, has a 0 oxidation state. So that hydrogen is getting reduced to be H2 gas. So you really need that H plus around because it's available to gain those electrons and become hydrogen gas. Okay, I hope this sort of helps you clear up what I saw as inconsistent in your molecular pictures and helps you think about net ionic reactions in general a little bit more.